What's with the XN? Alright, well, we're still missing a couple people, but we're gonna go ahead and get started here. So good morning, no, good afternoon. I already ate lunch. Good afternoon, everyone. Keep doing that. Alright, today we are going to finalize our triangle study this week with another related topic of the inequalities, except this time we are looking at two unequal triangles. We're comparing one to the other. But before we get to that in particular, let's go back to yesterday's work and go over the answers for that run real quick. So please go ahead and take that out and check your work against mine. So the first few is the triangle possible. 1 is yes, 2 is a no. And you can put a quick sketch such as this together showing that these two numbers are way too short to add up to that one. And 3 is a little bit different. 3 gives you two sides and says what's the range of possible values? What's the maximum third side we could have and what's the minimum third side we could have? I think maximum makes the most sense first. So let's look at that. If I know these are the two short sides, I know the third one cannot be bigger than their sum. So I can just add these together to get the maximum. But then for the minimum, what I want to do is say, well, what if the other side is actually smaller than, say, 36? I can go all the way down to make 36 be the biggest one. And then 36 can't be more than the sum of 17 and some mystery number. And so what you do is you would subtract 17 from 36 to find that minimum value. So you just add them and subtract them to get your possible range there. All right, 4, 5, and 6. Ranking from greatest to least. So 4 and 5, pretty straightforward. 6, you had to work back and forth between the various triangles overlapping each other to see, okay, how does this compare to that one? How does this compare to that? Because they share this triangle or they share this triangle. And what do you know about the angles involved there? Okay? And then for 7 and 8, we could work these out using the triangle sum and what we know of linear pairs. So we know that the three angles here, I should give this a name, call it alpha, terrible alpha. Okay, all right, these three angles add to 180, and we also know that alpha plus the 142, that exterior angle, will add to 180 because they are a linear pair here. Which means we could set those two halves equal to each other. We both know those groups add to 180. So we know that this group is equal to that group, and they share alpha. So if I subtract that off of both sides, I can find out that the interior angles are equal to this one exterior angle. And they've actually come up with a name for that shortcut. They called it the exterior angle conjecture. Right? It says an exterior angle is equal to the sum of the non-adjacent interior angles of a triangle. So that saves us a little bit of time. We can just take 142 minus 66 to get x. And same thing over here. Knowing it's isosceles, this has got to be the same. So we subtract and find 2x from the 158. And for number 9 here, what's wrong with this picture? I love these questions. So first of all, I can see this is 120 degrees. So a linear pair, that would be 60. This is 160, so with a linear pair, this interior angle must be 20 degrees. But then if you add them all up, you get 60 plus 20 plus 90 is not 180. Okay, you broke your triangle there. One of these numbers has to be wrong. Okay. Any questions on those guys? No? All right, then finally number 10 makes use of that exterior angle conjecture. Again, that's just a shortcut. You could also use triangle sum and linear pair. But either way, you're going to get down to saying that this angle plus PQS, so this angle up here, that measure plus x will be equal to the 2x over there. And then you can subtract an x from both sides. So we know the measure of PQS has to be x, which means those angles are congruent. If I have two matching angles, it must be an isosceles triangle. And we gave that statement a name, right? If two angles are congruent, then the triangle is isosceles. That's the converse of the isosceles triangle conjecture. Because the original isosceles triangle conjecture said if it's isosceles, then the two base angles are congruent. So we use that backwards there. So it's likely you guys would have explained this with more words. I used fewer. That's general idea that we're always working towards in mathematics, how to be as lazy as possible. That's why we have names for these conjectures, so that you can use them as shortcuts in your explanations. Okay? All right, last call for questions on this page. Yeah? All right, then let's jump to the new stuff for today, and that is similar triangles. Right? A different way to describe things not quite equal. They are similar. What does similar mean? Similar means they are the same shape, but of a different size. Okay? So I've scaled them down, smaller or bigger, but I've kept it exactly the same proportions there. So if it was a long, skinny triangle, I've just made a really bigger, long, skinny triangle, or a much smaller, long, skinny triangle. It's the same shape, the specific type of triangle, but now it's of a different size if it's similar. Compare that with congruent. Congruent, you remember, meant same shape and same size. They were exactly identical. But a similar shape means I took the shape and either like zoomed in or zoomed out to shrink it down. Which results in, for a similar triangle, we can say the corresponding angles are congruent, but the corresponding sides are proportional. So they won't be equal to each other, but the relationship between one pair of sides will match up with the same relationship between another pair of sides. Right? That's why the weekly homework lessons this week start you with proportions. That's like saying 1/2 is equal to 3/6. Right? It's an equation setting two ratios equal to each other. We typically see these as fractions. Fractions are just a specific type of ratio. But the relationship between 1 and 2 is the same as the relationship between 3 and 6. Right? You would double both of them. So you can go vertically. Right? You can say here to here is the same operation. You're still going times 2. Or we can go horizontally. We can say here to here. And here to here is both times 3. It's the same relationship horizontally or the same relationship vertically, however you want to think of that. So it really doesn't matter how you've set it up, so long as whatever you do on one side, you do on the other side, just like any equation. So we can use this to uncover measurements of a triangle that we don't know enough about. We don't have two sides to use Pythagorean theorem. We maybe only have one side. And it doesn't even have to be a 90-degree right triangle. I happen to use right triangles for my example here. Makes it a little clearer. Let's take a look. I'm being told triangle ABC, squiggle, triangle XYZ. This is our symbol for similar. Okay, just like we had the equals with the extra squiggle to be congruent, we use just the squiggle by itself, the tilde, to mean similar to. And the order here is important, as always. Triangle ABC is similar to triangle XYZ. It is not similar to triangle YZX. Okay? Because the orders tell you which correspond. Remember we said the corresponding angles? Which correspond to what? A is the first letter here. X is the first letter there. So those must be the corresponding ones. B corresponds to Y. C corresponds to Z. Which lets us match things up. So I know the side lengths here. Side Z is between X and Y. X and Y. So it should correspond to the side between A and B. So I know from the given information that it must be 5 corresponds with Z. And so I could write that proportion, setting up Z corresponds with 5. Okay? So here I'm setting the large triangle over top of the small triangle, matching corresponding sides. So for the other half of my equation, I better make sure I do the same thing. Large triangle on top of small triangle. So let's use a number I do have for the large one, 19.5. The corresponding one for the small one, that's 13. And now I can just solve for Z like any other algebraic equation. So I want to get Z by itself. It's divided by 5. Let's do the opposite and multiply by 5. So I got to do the same thing to both sides. And so my Z is equal to 19.5 divided by 13 times 5. And I happen to know from earlier 19.5 divided by 13 is 1.5. 1.5 times as big. Okay, I enlarged the triangle by 50%, as it were. And so 1.5 times 5, quick mental math, a half of 5 is 2.5. 2.5 plus 5 gives us 7.5. So my length of Z there is 7.5. Any questions on how I did that? All right, then let's find Y. And Y, we could set it up in the exact same way. We could do big over small. But let's show that you can do it whichever order you want. Let's try one side against the other. We'll stay within the triangle here, and we'll do Y over 19.5. So in this case, I have the middle length over the long length. So on the other side, for the other triangle, I have to go middle over long. Make sure they're in the same order there. 12 over 13. Right? So that horizontally, I have the corresponding Y to 12, 19.5 to 13. Just like we had corresponding sides vertically here. Now my correspondences go horizontally there. It doesn't make a difference. You're still going to multiply both sides. And if the 12 had been down here, I'd be multiplying by 12. So it would just switch positions here, which doesn't change the multiplication. It's commutative that way, right? So again, 19.5 divided by 13, I know that part is 1.5. And so 1.5 times 12, half of 12 is 6, plus the 12 again gives me back to 18 for Y. Questions on how we did that one? No? Alright. Well, if you haven't already, please take your pencils out and get your calculators ready because I'm going to challenge you now with a question. So I need to see everybody's answer in the chat. Here's what we're going to do. We're going to apply this. A very common situation for similar triangles is in casting shadows. Well, okay, the triangles themselves aren't casting shadows. But when something does cast a shadow with the sun's rays, you've got the object itself and the shadow on the ground creates a nice right triangle here. And we can use that to measure things indirectly. It would be very impractical for me to try to climb up and measure the height of this tree precisely. But if I know how tall I am, and I line up my shadow with the tree there, I can measure my shadow's length and the tree's shadow length. And you can see these are right on top of each other. They've got to be similar triangles because this is the same angle from the sun here, and they're both perpendicular. So we've got two right triangles. So here it is as a diagram. Okay, here's the height of the tree. Here's the height of me. Let's pretend I'm 5 feet tall exactly. A little short for myself. So maybe that's your height, right? You're 5 feet tall. Your shadow length right now is 7 feet. And you are 10 feet from the tree. So careful, 10 is not the length of this triangle. It's the length of this portion. So you're going to have to add this together to get the length of that triangle. So set up a proportion from these similar triangles and tell me what is the height of the tree. That's your challenge. You have 2 minutes. Go. All right, time is winding down. Let's start to see some answers in chat. No one? All right, let's break it down step by step. I need 4 numbers to fill in my proportion here. I like to start on the left-hand side, and I usually start with what I'm trying to find. So, what number goes there? If a number. What do I put here? What am I looking for? What's my variable?
I don't know, bitch. You tell me. Fuck.
What was that? Guys, what am I trying to solve for here?
H.
H. There you go. Thank you. And H is the short side of the large triangle. So what do we want to set H over top of? We can either set it with the corresponding side of the small triangle or with the other long-sided triangle. Up to you. What number would you like to put beneath H?
Five.
5? Okay, so we've got the short of the large triangle and the short side of the small triangle. So keep that in mind. We're going large over top of small. Now on the other side. I started with the large triangle. I need the other measurement of my large triangle. What's that going to be? This full length here. How long is the tree's shadow? There we go. Litsy's got it in chat. 17. Yeah, come on, guys. You had 10 and 7. And then that's the long side, or that's the side of the large triangle. So below it, I need the corresponding side of the short triangle. So what goes down here? Seven. Thank you, Litsy. So there is our proportion setup. All we need to do is solve for h. Multiply both sides by 5. H is equal to 17 divided by 7 times 5. Or if you like, 17 times 5, then divide by 7. That order doesn't make a difference. And you should get something like 12.14, I believe, approximately. So that would be in, what did I say, feet? So that tree is 12.14 feet tall. Okay, questions on how we got that? Yeah? All right, then you're on your own for the rest of these exercises. Doing 1 through 4, fairly straightforward ratios there. 5 and 6 have this right triangle, just like we were working with before. And 7 and 9 are doable, but 8 relies on a circle property that we haven't gotten to yet because we're going to do circles after Thanksgiving break. So we'll be able to come back to this probably sometime later. But if you'd like to read ahead in the big fat notebook and try to figure out how that one would work, you're certainly welcome to. But you're not required. You can go ahead and skip number 8. Okay? So that's going to do it for the stream for today. Go ahead and get started. You've got the rest of the period to work. Let me know if you have any questions.